What we're interested in talking about today is what this has to do with the phenomenon of resonance. Everybody knows at least one case of resonance, I hope. Uh, a little kid is on a swing, right? Bing, back and forth, and they're very, very little, so they want to push. Okay. Well, everybody knows that to make the swing go, a swing has a certain natural frequency. It swings back and forth like that. It's a simple pendulum. It's actually damped, but let's pretend that it isn't. Everybody knows you want to push a little kid on a swing so that, they go high. You have to push with essentially the same frequency that the natural frequency of the spring, of the swing is. In other words, now it's automatic because when you come back here, it gets to there, and that's when you push. So automatically you time your pushes. But if you want the kid to stop, you just do the opposite. You push at the wrong time, and anyway. Okay, so that's resonance. Of course, there are more serious applications of it. It's what made the Tacoma Bridge fall down, and I think movies of that are now being shown, not merely on television, but in elementary school. Resonance is what made, okay, more resonance stories later. So my aim is, what is this physical phenomenon that to get a big amplitude, you should have to match the frequency? What has that to do with the differential equations? Well, the differential equation for that simple pendulum, let's assume it's undamped, will be of the type y double prime plus, I'm using t now since t is time, that will be our new independent variable, plus omega naught squared is the natural frequency of the pendulum or of the spring or whatever it is that's doing the vibrating. And now yeah, question? Any questions? What we're doing is driving that with the cosine with something of a different frequency. So this is the input, or the driving term as it's often called, or sometimes called the forcing term. And the point is, I'm going to assume that the frequency is different. The driving frequency is different from the natural frequency. So this is the input frequency. Okay, and now let's simply solve the equation and see what we get. So if I write it using the operator, it's d squared plus omega naught squared applied to y is equal to cosine. It's a good idea to do this because the formulas are going to ask you to substitute into a polynomial. So it's good to have the polynomial right in front of you to avoid the possibility of error. Well, really what I want is the particular solution. It's the particular solution that's going to give me a pure oscillation. And the thing to do is, of course, since this is cosine, you want to make it complex. So we're going to complexify the equation in order to be able to solve it more easily and in order to be able to use those formulas. So the complex equation is going to be d squared plus omega naught squared times, well, it's going to be a complex particular solution, so I'll call it y tilde. And on the right-hand side, that's going to be e to the I omega 1t. Cosine is the real part of this, so when we get our answer, we want to be sure to take the real part of the answer. I don't want the complex answer. I want its real part. I want the real answer, in other words. The really real answer. The real answer. Okay, so now, without further ado, because of those the problem has been solved once and for all by using the substitution rule. I did that for you on Monday. The answer is simply e to the I omega 1t divided by what? This polynomial with omega 1 substituted in for d. So it's sorry, I omega 1, the coefficient, complex coefficient of t. So it is substitute I omega for d, I omega 1 for d, and you get I omega 1 squared plus omega naught squared. Well, let's make that look a little bit better. This should be e to the I omega 1t divided by, now what's this? This is simply omega naught squared minus omega 1 squared. But I want the real part of it, so let's, as one final last step, the real part of that is what we call just the real particular solution. So yp without the tilde anymore. And the real part of this, well, this is cosine plus I sine, and the denominator luckily turns out to be real. So it's simply going to be cosine omega 1t, that's the top, divided by this thing, omega naught squared minus omega 1 squared. In other words, that's the response. This is the input, and that's what came out. Well, in other words, what one sees is that regardless of what natural frequency the system wanted to use for itself, at least for this solution, what it responds to is the driving frequency, the input frequency. The only thing is that the amplitude is changed, and in a rather dramatic way, if omega 1, depending on the relative sizes of omega 1 and omega 2. Now, the interesting case is when omega 1 is very close to omega, the natural frequency. When you push it with approximately its natural frequency, then the solution is big amplitude. The amplitude is large. So the solution looks like the frequency, the input might have looked like this. Well, it's cosine, so it's sort of start up here. The input might have looked like this, but the response will be a curve with the same frequency and still a pure oscillation, but it will have much, much bigger amplitude. And it's because the denominator, omega naught squared minus omega 1 squared, is always 0. So the response will instead look like this. Now, to all intents and purposes, that's resonance. You're pushing something with approximately the same frequency, something that wants to oscillate, and you're pushing it with the same frequency, approximately the same frequency that it would like to oscillate by itself. And what that does is it builds up the amplitude enormously.